upload also the videos online. I decided to give a lecture on the foundations of robot learning. So we are going to discuss a bit. Let me move to the second. Okay, yeah. Let me move to the outline already. So we are going to see a bit the landscape of robot learning, of the robot learning field. We are going to talk about modern imitation learning. We're going to discuss reinforcement learning, but everything with a mind on applications on robotics. So this is not going to be a pure machine learning lecture. We are going to discuss also a bit more how does this get applied to certain scenarios in robotics, which part of these methodologies are also coming from my lab at TU Darmstadt. And finally, we are going to touch also a bit on foundation models, since this is currently a huge trend in AI, and obviously in embodied AI and in AI-powered robots. So we are going to get a lot of information. I have structured this lecture into 4 parts, as you see. And I would like to take, so it is a long lecture, as you can imagine, because I try to cover a lot of things and give you a bit of idea about everything. But I would like to make pauses after part 2, after part 3, and then in the end to take some questions from you. So feel free to also write questions on in the chat. Or we will make short pauses of like 5 minutes or so to in between to if you have targeted questions to cover those, and then continue with the rest of the lecture. So let's first try to understand what is robot learning. So robot learning is the field that uses methodologies from machine learning, and in particular supervised learning, reinforcement learning, and unsupervised learning methods to make robots acquire skills through imitation and interaction with the environment. The ultimate goal that we have as AI researchers and robotics researchers is to build some sort of general purpose, which is also a question mark of how general you want this purpose to be, embodied intelligence into physical bodies of mechanical systems, the ones that we call robots, by learning to make sequential decisions in the physical world. And obviously, this requires an interdisciplinary contribution of different fields, obviously, algorithms, a lot of data. The backbone should be, and it has been actually powered by very powerful compute and also very good hardware. We are living actually now in a period where we can see that the robotic hardware is more accessible than ever. And this is great times to do robotics currently. So we are very excited also to have Rick for that reason. So how far are we for having embodied artificial general intelligence? The generality for me, if you ask me, generality basically describes a robot that, for example, can do a sequence of actions in an unstructured environment like a house environment without having seen every possible aspect of your house before. Maybe it doesn't do all the tasks that you would want it to do, but this is the level of generality that I would be, let's say, happy with in the actual environments to happen. How far are we? Well, we have not achieved it yet, and even if different startups and what you hear from VCs, etc., hovering around, it seems like this is to be solved in the next year or so. But I can tell you from my experience, and I think many of the researchers at RIC would agree on that, we are very far from the vision still of AI robots living in our environments, collaborating with humans beyond some very specific settings, I would say. And so let's see a bit the state of the art. We know that with classical control, and if we know the dynamics of the systems, we can do amazing things. Like you have seen this robot, it was called Atlas from Boston Dynamics. Now it is retired because this was basically the system was using hydraulics, so now they moved to a different way of controlling the robot, but we are not going to talk about hardware here. What is important to know is that you could do such amazing things even with classical methods, with classical control, which was very robust, but hard to program and do these in an open world environment. On the other hand, we have robot learning methods that exist for quite some years now, right? I would say more than 15 years now, these methodologies exist. And they became essential in some sense for contact-rich tasks where especially modeling the dynamics is very, very difficult, like, for example, here, wiping a mess. But robot learning is adaptive. It is adaptive. It has to be adaptive, but it is very data hungry. So we can see now that we can solve agility with physics, with known models, but we need learning to solve open world manipulation and open world interaction. And yeah, general question in general exists also in the field of robotics of why do we need robot learning? And we can see that by experience, by collecting experience and also looking at the paradigm of how humans learn, having data can really allow you to exceed, in some sense, the upper bound of some algorithms or like learn from many, let's say, classical algorithms, like planning algorithms, and then distill this information into a powerful model that can, in the end, be very fast in making decisions, being reactive, and so on, and even help us alleviate the problems of, for example, modeling every aspect of the world, because in simulation, many things can be, let's say, modeled nicely on being like left aside because maybe they don't matter, but in the real world, even small details matter. For example, if the friction of a terrain changes slightly, this will change the locomotion pattern that the robot has to do. And if this is, it's hard coded based on specific physical parameters, then it's not going to work at all, right? Of course, other problems that we have to take care of is that the environments and tasks may change. Maybe the structure of the policy that we're using is limited. Maybe our solver, even optimization solver that we are using, might be wrong for the problem at hand. Some assumptions that we do when we try to solve a problem with classical methods might not hold. Most of the times we may need separated perception, planning, and control pipelines, while now we see that robot learning tries to push into a unified framework where perception, planning, and control becomes even a single end-to-end architecture or a modular architecture where these things at least intercommunicate in a more, let's say, fluid manner. So that they can adapt to each other without being rigidly distinct modules in the system, in the robotic system. And I don't know why this video lags here, but I wanted to show you here is that in the end with learning, you can do things like parkour, right? Taking also a connection to the paradigm about the locomotion that I described before. You may not have seen these structure before, but because you have learned in a certain way, in this particular case with the reinforcement learning that we will discuss later, the robot is able to pass through this difficult path. Now, if we see the evolution of robot learning, we can see three distinct periods, but also methodologies. Of course, there are interconnections, and we are going back and forth in the research field of robot learning. We start with the exact supervision, which is imitation learning, which requires some level of human demonstrations. Usually, these data have to be very high quality, so they have to be smooth, of equal length many times, with very good success, not very jerky, and so on. They are very difficult and expensive to collect, and usually it's hard to scale because, well, you need to collect this data usually from humans. So yeah, how can you find so many humans and so many robotic platforms to really collect all this data? But yeah, it has, of course, its pros. And on the next step, we have trial and error learning, that is reinforcement learning, which manages to generate on its own large amounts of synthetic experience, usually done in simulation because it is safer. It requires, though, careful reward shaping. We will discuss later these notions, which is the signal that basically encourages the agent to keep collecting a certain way of behaving, and exploration, which is basically trying to figure out what to do in a certain environment. And finally, one problem is that as I said, most of reinforcement learning research is done in simulation because it is safer to explore there. We don't have to break our robots, but there is the sim to real gap, and then we have to address safety and robustness of these policies when they get transferred into the real world. And finally, we have self-supervised methodologies, which have been used for training large foundation models. Usually these require internet-scale multimodal data, mainly visual and language data that we can find on the internet. They try to provide the general representations without any labels, so everything happens on a token level, so on the embedding space of our network architecture. So we don't need to annotate the correlations, let's say, between language description and pixels, right? This happens in a self-supervised manner by the training of these networks, but they need physical grounding in order to produce executable actions. So here you can see a high-level comparison of what we discussed between imitation learning, reinforcement learning, and foundation models. And obviously, the potential that they have, for example, for imitation learning, they're upper bounded by the demo quality that we provide. For reinforcement learning, it can go beyond the expert level, but then it is subject to the reward design that you do. Foundation models promise to deliver zero-shot generalization because of the intercorrelation between language and vision, and hopefully also robotic actions, as we will discuss later. But the main challenges in imitation learning is the distribution shift. In reinforcement learning is safety and sample efficiency. How much should I explore in order to understand if I have learned something, and then is this policy that I learned safe? And for foundation models, grounding into the physical world, is this action really executable? Can I safely interact with something right now? Are the preconditions, for example, correct in order to execute an action? And obviously hallucination, because you don't really have very good ways to steer these models into producing safe and realistic actions. And you have already experienced it when you interact, for example, with ChatGPT, depending on how you ask and how often you ask. So this also the memory component is very prominent here. It may start hallucinating. And if this happens when a robot interacts with the environment, it can have, of course, hazardous effects. So let's go into modern imitation learning. But before going into modern imitation learning, let's just recap what is the main idea behind imitation learning. We just said you need to collect data. And one of the first applications was in autonomous driving. And even autonomous driving with images. The idea is that you collect the observations that are let's say the image of a human driving a car, and the actions of the human that are the steering wheel angles. You collect this training data, and then you have a regressor that it is able to map observations to action. So you want to learn this deterministic mapping from with a pi. We will, for now on, with pi theta, we're from now on going to represent the parameterized policy that we try to learn. Theta are the parameters of this policy. Policy is a controller. So in machine learning, in particular in reinforcement learning, and imitation learning with pi, the controller, in essence, or like the behavior generator, is called policy. We can make an initial assumption that we will, in a few slides, are going to decompose. You can assume that since you want to solve a supervised learning problem because you have the data that you try to learn, you have the labels, which are the actions, you can hope and assume that the data are independent and identically distributed. The objective that you try to optimize is the very simple mean squared error between the actions that you have collected and the ones that your regressor is trying to predict. The pros is that this is very simple, stable, and works with minimal data, especially if your task that you have to solve is also, let's say, restricted. So really, you can learn nice things in a restricted task space of your robot. But of course, it has limitations. It doesn't have a recovery mechanism if an action goes wrong, and if the recovery action has never been encountered, it doesn't know how to recover. And usually with this kind of, let's say, simple models, simple regression models, and using the MSE error for your loss function, you assume a unimodal behavior. So there is only one way of solving the problem, which again, for certain tasks and domains, it might be perfectly fine. But for open world, for example, robotic behavior generation, it might be problematic. So in particular, we are interested in behavioral cloning, where exactly the goal is to learn a behavior. So we, for example, in the case of, let's say, driving here, we can collect the state actions as trajectories, and then these are used in a supervised learning fashion, as we said, in order to map the state that could be image or the actual state that you could get, for example, maybe from a simulator or some motion capture system. It maps into the controls that in this case for the driving is the steering direction. We can also do this with images, as we said. For example, you can use a deep neural network to process high-dimensional images, pass them through some convolutional neural network, and output continuous controls. And this has been research that has already started from the 90s or like 89 already with the Alvin autonomous driving car. However, what is important to understand is that behavioral cloning is not standard supervised learning. It violates the fundamental assumption of this of statistical learning, that it is this IID assumption that basically the samples are drawing independent. In robotics, the data are not independent, so they are basically sequential, and the state t+1 that you arrived after doing an action A depends on your state, on your previous state, right? Therefore, this is a very important property that basically takes you away from all the guarantees that you can have from statistical machine learning when it comes to studying supervised learning. Of course, we also assume that the expert data contains only good behaviors. Then, therefore, whenever you do even the smallest mistake, then you end up in what we call covariate shift. So you get a distribution shift, as we will discuss in a while. And this mistake creates a cascading failures that end up basically completely diverging from the data that you have, from the trajectories that your expert has provided you. And this is very interesting because in general, when you will be training a policy, you may see the training loss going down, and then you say, okay, it learned, but this doesn't mean that the performance at test time is going to be good. Because even some millimeters of error, let's say, or some small degrees deviation or rads in the steering angle, and can really take the car out of the desired demonstrated trajectory. So we can really say that behavioral cloning is a cliff walking problem. So if you cannot recover, you will end up off the cliff, right? This is basically what we call domain shift or covariate shift in classical machine learning. Why does this happen? We have already hinted to some things. The problem, first of all, is that the policy only sees the good expert data that you provided. It doesn't know how to recover from bad state. It doesn't even know what is a good state or a bad state, right? The expert will never go to a bad state. Why would they, right? And also we said also before that we want the data to be smooth and nice in order for the regressor to learn meaningful behavior. Once we make one mistake, we can go out of distribution. And here you can see this example. Here is the trajectory. Here is you start very nicely from the same state. You take an action and you start deviating and deviating. This doesn't mean that always the next action is very wrong, but this is what we call the compounding error, right? So this error keeps accumulating, and then you drift away from the expert trajectory. Now, another reason we're going to discuss now why regression fails, and I will try to give you an idea of what this graphic that comes from the diffusion policy paper tries to represent. First of all, the MSE loss can be seen as a problem because you try to always, if we minimize the mean squared error, we are estimating the conditional expectation of taking an action given a state. And if you have a bimodal distribution, let's say you can go either you're in front of a tree and you can go either to the left or to the right, and you basically take the mean, it might tell you to go in the middle, right? So especially when we are trying to figure this kind of multimodal decisions, the MSE loss is going, and your data set is very diverse in this regard. So you have seen both, let's say, directions of motion, then it will become problematic, and it's evident that this kind of learning is not really good. So what one other problem is that with standard behavioral cloning, with regression models, we can predict a single action, and this is only one guess, but if it is off, then this error is locked and you cannot recover, as we discussed also before. Now, we can say that this kind of regression models are explicit policies. They take, as you see here, an input, an observation. Let's say that this is an image. It goes through some regressor. It could be any type of regression. It could be a neural network. It could be, least squares regression models. It can try to output an action, and this action could have different types of representation. This is not limited. It could be, for example, a scalar regression mapping into a single Gaussian. It could be a mixture of Gaussians regression, or even categorical distribution when you have discrete actions. And on the other side, you have implicit models. The one type of models is the energy-based models, which they take as an input the observations and the actions, and they try to predict a value that we call energy. That this value shows how close you are. Low energy means that you are very, very close to the demonstrated data. And when you try to get the action that minimizes this energy, you can get the best action that follows, let's say, the observations. And finally, you have the diffusion model, the diffusion policy that operates on the gradient field. So you can say that basically this is the vector field of the energy landscape, which treats the action generation as an optimization process, and they are refining the action over some denoising steps, as we are going to discuss. And it corrects the mistakes that come from just predicting a single action internally before you apply this action onto the robot. These types of policies are very expressive, and they are able to model the multimodality in the distributions. Of course, you're going to tell me also mixture of Gaussians and can, for example, do similar multimodal modeling. However, there you need to know, for example, the number of modes, right? I'm going to discuss in a while such work that got produced, for example, from our lab. And this could be seen, for example, as a caveat. However, you can also have a combination of diffusion models being distilled, for example, into mixture of Gaussians for faster inference, so that you don't need to do always these denoising steps that might be slow, although now research has been moving forward, and we can do faster inference also with newer models, the so-called flow matching models that I'm not going to discuss very much. I'm not going to discuss them today. So this is now why in modern imitation learning, we use generative models. Instead of predicting a single action, like we have seen with the regression models, we learn a joint distribution of an action given a state. For that, what do we need? We need to try to learn this distribution, the p theta, that tries to match the data distribution. And once we get that, we can generate novel data given that we have this distribution. Types of models that we can use in order to do what we call distribution matching are the generative adversarial networks that have been used for some years, although they have stability issues, the variational autoencoders, and most recently, as we said, diffusion models and flow matching models that are not depicted here, that can capture these more complex multimodal behaviors, and they can also be steered as they can also be conditioned. So you can really steer, for example, which mode, for example, internal mode, you want to, hidden mode, you want to select and execute. So earlier approaches used variational autoencoders to compress the high-dimensional world, the state representation, the X in this particular case, into a latent space Z, making the learning problem tractable. These models are also called latent variable models, and in order to produce an action, we sample this Z from the prior, and then the decoder maps the state and the latent vector into an action. During the training, we use the evidence lower bound, the so-called elbow objective, which tries to balance the reconstruction loss with the KL divergence between the approximate posterior and a prior that we have defined that most of the times is a zero mean Gaussian model that we introduce. So everything is fine, but of course this prior usually enforces a unimodal behavior. However, it can generate actions once you are able to match the data distribution well enough. And also quite, let's say recently, like 2 years ago, VAEs were still quite useful for imitation learning. The action chunking with transformers is a technique that builds on conditional variational autoencoders. It introduces what happened here. Of course, you have an encoder, you have a decoder, but the method here introduced two architectural priors, if you want, to solve the drift problem that happens in imitation learning, especially if you have also learning from images. And in particular, here you can see that they have 4 images, 2 on the end effectors, and then another 2 that oversee the scene from 2 different perspectives. So how do they try to overcome the drifting problem in imitation learning? The one aspect is the action chunking. Basically, what we do here is that we predict a sequence of action from T to T plus K, rather than just a single step. And this basically reduces the effective horizon of the problem and provides also a stronger let's say, gradient signal for training the model. And the second part is that they introduce temporal ensembling. So at each step, we average the predictions from overlapping chunks. And this acts in some sense as a low-pass filter that smooths out high-frequency jitter from the BAE. This method have produced some interesting results. This is playing, yeah. So they used for collecting the data, they use the Aloha system that you might be familiar. This is basically a leader-follower system where a user has the same exact robotic arms on their side. You cannot see them. They are on the other side of the table usually. And they are manipulating the arms. So they are moving explicitly the joints of the arms. And these are directly with very low latency being transferred on the coupled robotic system. And this is how they can produce very high quality data to solve very challenging manipulation tasks, like you see very smooth and precise manipulation with this really low cost hardware that has also a lot of mechanical noise. But they show here that even with not so perfect data, by using also this temporal ensembling, you are able to smooth out a bit the noise from the learning. Of course, still you need to become very skillful to collect the data. It's not that anyone can collect the data and that you can learn from it. Still, there is quite some noise. But as I told you before, the problem of the VAs is that still they are basically in some sense bounded by also the prior that you introduce. We try to overcome this problem by leveraging a mixture of variational experts. So we're trying to basically learn multimodal behavior, especially for tasks that include humans, which their intent could really be multimodal. A human might want to pass you, for example, a glass of water with many different ways. There's not only one way. I can use my left hand, I can use my right hand, I can do it in many different ways. We looked at modeling the latent space dynamics of interactive tasks using the mixture density network that uses the idea of variational autoencoders, but trying to structure the latent space so that it can capture different modes. In these mixture density networks, rather than predicting the single distribution, we try to predict multiple distributions and which are predicted along with their mixture coefficients, which is the equivalent of predicting a Gaussian mixture model rather than a single Gaussian. So we use this MDN network to learn multiple latent policies from human. This started with using data from human-human interactions. So we learn these from condition on the human input. And then these latent policies are then combined to obtain a conditional distribution in the robot's latent space based on the human input. The conditional distribution is then used to regularize a variational autoencoder trained on the robot trajectories. This allows us to have an informative prior over the robot VAE in order to capture the dynamic nature of the human interaction, rather than using this unimodal standard Gaussian prior with the zero mean and unit variance that we use in the standard variational autoencoders that we saw before. And here we have introduced also auxiliary losses, like reconstructing the robot's trajectory based on the human's observations in order to be able to have reactive motion generation based on the human input. And we found that this is very crucial to learn more accurate and reactive behavior rather than just using directly the MDN predictions as a prior for the KL divergence. And also we found that by adding these auxiliary laws, we can also mitigate the distribution shift that occurs during test time when only human inputs are observed, and you eventually just want to output the action. And we also have found that these mixture density networks, one issue that they have that will hopefully get mitigated later on with diffusion models that we will see. In these particular cases, it is very easy to have mode collapse if you don't introduce any regularization, so you may lose all the modes and then just learn the single mode that it's maybe the one that is more dominant even in the data that you have, because you cannot always have balanced data sets. To prevent this mode collapse and ensure that the predicted policies are distinct, that we have basically these distinct modes, we additionally incorporated a contrastive loss. So as you see, in order to, in the end, make this method work so that you can do human-robot, let's say, handovers, as you will see in a while, we had to introduce additional regularization objectives in order to ensure that you don't lose multiple modality and that you are reactive to the way, for example, the human behaves. So internally, this model learns to predict what is the intention of the human, but also to react in case the human changes their behavior. Now, the current, let's say, king of generative model is the diffusion models, as we said. In diffusion models, instead of predicting an action in one shot, you start from random noise, and you try to iteratively denoise this state, this action, so that you reveal a clean action from the trajectory. By doing so, you are learning basically these conditionals, and by using these conditionals, you can iteratively use them to refine how fine-grained, let's say, the prediction towards a sample that comes from the data distribution looks, and therefore from that you are able to get very high fidelity samples, and we have seen these also in image generation. One of the papers that first tried to use the diffusion models for control were the diffusion policy, where they, in essence, took the ideas here and let's say that X is the state. They have also introduced the action as an additional observation into the system. So the system has to take as input the observations and try to predict the actions into an effective horizon again, in a similar way as it happens also with the action tracking transformer. In this diffusion policy paper, they have introduced different ways of doing these modeling of the diffusion policy. So the first architecture is CNN based on the UNet models, the UNet architecture that has been used thoroughly in computer vision, and it's actually a very stable way for executing the diffusion process. And alternatively, you can have a transformer-based architecture. During the diffusion policy, what you do is that you iteratively requery these networks by introducing at every time step, sorry, let me go back to the diffusion part. So at every time step, even in these diffusion policies architectures, you are trying to get this conditional xt minus one and of course, obviously, the respective action with respect to the previous xt, to the previous state. And you pass through this model several times. The k parameter here is the number of diffusion denoising steps that you want to do. And they showed some very interesting results. For example, putting like the sauce on pizza and so on, or they have introduced also this push T task that has become kind of a standard for diffusion model learning and benchmarking. But one problem that we have found is that, in essence, the data that they have used were not inherently multimodal. And there has been some more recent research that showed that basically a lot of the gains that we see in using diffusion models for imitation learning, even if the data are not multimodal, is by this iterative optimization that happens internally when you do the denoising of the policy. From our side, we were also very interested into using these models, and we have used these models for learning grasps. And actually, since as I already told you, this denoising process is basically an optimization process, it is very interesting that you can couple it with more classical trajectory optimization methodologies in order to do things like predicting a grasp and the respective trajectory for grasping an object in a single shot, let's say, instead of first sampling some grasp poses and then eventually seeing if any of these samples is good enough, if I can find the trajectory in order to execute this path. So we call this SE3 diffusion fields. They live in SE3 because the grasps and the trajectories that we try to introduce live in the SE3 space, or in the 3D translation and rotation of the task space of the end effector of the robot. And what we can basically do, the parametrization is a neural network that tries to learn the energy field of the grasps in the over, let's say, the 3D shape of an object, and how we can then query, how we can learn basically these models. We can start from an initial noisy grasp in SE3, and then we can learn this energy function, or if you want to call it cost function, and in particular it's gradient, because we are, as we said before, in diffusion models, we learned that gradient field by diffusing this noisy pose till you find until you recover a sample from your target distribution. The network that we trained in order to do this jointly learns an implicit sign distance function representation. This sign distance function representation is a neural representation that basically learns if you query with a point, it can tell you basically if this point belongs on the surface of this object, or if it is inside this object or outside of this object, not on the surface. So it can give you all these level sets. It's an implicit function, and it has been thoroughly used as a 3D representation alongside now, of course, NERVs and Gaussian splats. It's among the dominant volumetric representations that we use in robotics. So with this SDF, we can capture implicitly the shape, the shape of the object, and together with that, we try to predict the energy of the grasp energy from this multimodal grasp. Because, for example, in this glass, you can, as you can imagine, you can have tens or even hundreds possible grasps, and we learn this model while also adhering to the geometric space that we are working on, which is the SE3 manifold, and we have used methodologies from Lie algebra. This is why we have put the SE3 target on the name of our methodology. So now that we have these SE3 grasp energies, we can use differential forward kinematics to connect the configuration space of the robot to the SE3 task space. So you can do this forward kinematics to really sample and see with which configuration can I end up in an end effector pose that really satisfies the necessary target grasp pose that I want to execute. And with this way, we can effectively jointly optimize, as I told you before, both the grasp pose and the trajectory through this joint optimization problem. And what is very cool about representing the grasps as this kind of energies and costs is that you can effectively compose them with other cost functions that could be learned or could be handcrafted ones, like, for example, avoiding collisions. And we can, for example, here as an example of performing pick and place in different configurations of the scene, where the whole trajectory is resolved in a single optimization problem. So in this case, we can basically generalize grasping in different scenes without needing necessarily to collect data in all these scenes. So this makes this method highly generalizable. This brings me to the end of this part, and I would like to ask if you have any questions. I don't know how is this moderated also from the in-person attendees, but if you want to ask something about imitation learning right now, please, or the first part, please do it now, because then we will proceed with the part of reinforcement learning.
Okay, so maybe we can start with KIT. Are there any questions at KIT? No question? Okay.
Not for the moment.
What about TU Munich?
Questions at the morning. Well, a moment.
All right, TU Berlin. Also no questions. Okay, then for the people online, you can also speak up or post something in the chat.
Yeah.
Wait a little bit, and otherwise we will have to move on.
Okay, if
everyone is happy, so I guess you can.
yes, okay, yeah, I will continue. All right, so let's go to the next part, learning from experience. Of course, we can recap again, why is imitation learning so limited? Why is it a problem? So as we said before, it needs experts. For example, it needs humans to collect the data. Here you can see a version of the Aloha system that we saw before in the ACT methodology, being mobile. So they put it on top of a mobile base, and the human had to move around and collect data with this now huge system, right? So you can understand that also your reachability with such a system, it's very difficult, and also you have to really be very well trained in order to do this. As we said before, we cannot go beyond the expert level, might not be enough for achieving the super intelligence that we would like our robots to have. And ideally, we would want artificially intelligent agents to be able to learn autonomously on their own. Even if initially you give some demonstrations, then it should be the case that an intelligent agent is able to adapt and keep learning autonomously given a specific goal that they have. And here you can see a slide from the talk of Oyer Mess that now is in Microsoft. He used to be PhD student of Wolfram Burgert. When he talked about embodied intelligence with foundation models, I think it was also kind of a joke, but I don't know how much of a joke it really is. In order to make a very fancy rockstar robot demo, you need to collect expert teleoperation robot data. Teleoperation in any way, it can be that you use Aloha systems or you use some sort of teleoperation system. If it is not working yet, you should keep collecting more and more data until extrapolation, so the generalization, becomes actually interpolation. And you have to train test the same day so that you don't change anything in your setup. Otherwise, you have to start all over again, because if something moves even some centimeter, then you go out of distribution. You have to collect data all over again. And this is basically the caveat of imitation learning. Now, let's go to the foundation. So we want our agents to be learned to be able to learn on their own, in order to achieve their goals and have also an understanding of the consequences of their actions. And this is the goal of reinforcement learning. The goal of a reinforcement learning agent is to find the policy that maximizes a cumulative reward signal gathered through direct interaction with the environment. So the agent is acting in the environment, and every time it acts, it collects a signal that tells it whether the action that it has taken is good or bad. And your long-term goal is that the collection of this reward towards achieving your goal will be maximum. RL does not require an expert per se to provide the data. I see something in the chat. No, the caveats of imitation learning can, so the question here is, do you think the caveats of imitation learning can be solved by a better platform? Is it not using Aloha? No, they cannot be alleviated by that, because if you see, we can actually have expert teleoperators in amazing systems, like this type of Aloha teleoperation is being used for robotic surgery since ages. And yet, of course, the system is very, very difficult, but still we have not managed to, to automatize fully these operations. It's not in the hardware itself. Of course, better hardware always helps. The low-level controls also can help. However, if the, let's say, intermediate layer that decides what is the next pose really drifts, there is nothing you can do with your platform that is going to make things work better. And eventually you can think also of something else. If a human can teleoperate Aloha to do something very complicated, but that the network cannot really replicate that or recover from that, this shows that the brain that the human has, the brain is there, but it's just that it's not easy to distill the decision making of the human into the hardware. Of course, as I said again, being able to have smoother executions because of better motors and better hardware can make our life a bit easier, but it's not solving the intelligence problem. Now, to go back to the reinforcement learning, as I said, reinforcement learning does not require an expert. It requires the agent to create its own data by taking actions and observing the outcomes of their results. And this can be rewarded or penalized by a scalar that is given to it. Of course, you as an expert have to design this function that tells you if you have achieved your goal or not. It can be, of course, as simple as just giving you a reward if you achieve your goal, but we know, and we were going to discuss also in a while, that this reward function usually has to be more dense so that it can guide you better. So as we also said before, the objective of reinforcement learning is to maximize this total expected cumulative reward over time, which is the sum of the future rewards. So basically the agent says, I have now this policy that I have trained with all this data that I have collected so far. If I use this network without updating these parameters anymore, if I continue using this policy from now on till let's say, I don't know, some time horizon. It could also be forever, but let's say that we have now a fixed time horizon. If I continue using this policy, will I get the future maximum rewards and achieve my goal? If this is optimistic, the agent will try to keep using this way of behaving. But if it's pessimistic, so if basically this reward is, let's say, low, this cumulative reward is low, it will try to change its behavior. So some specifics just to give you a bit of intro of classical reinforcement learning. The formalization of a reinforcement learning problem is done through the modeling of a Markov decision process. It is Markovian because they use the word Markov there because it adheres to the Markovian property that tells us that all you need for predicting the future is just the current state. Only the basically current state is the sufficient statistics that you need. You don't care about the previous history that you had of the stated actions that you have done before. So your current state is sufficient statistic in order, it summarizes basically everything that you need to know about the past in order to understand how to act into the future. This is very nice when you have a fully observable state, basically that you know with precision what is the exact state of an agent. To give you an understanding, if you can just know the position of an object through an image, you don't really know the position of the object, right? You just know pixels in a two-dimensional manifold. But if you put OptiTrack, like motion capture markers on the system on a super well-calibrated motion capture system, then you can get, for example, the state, or of course in simulation, you can really get the true state of these objects. In the case that this is not true, then we have observations, and what we have is a partially observable Markov decision process, but we do tricks in order to make it look like a Markov decision process, where we say the state is not really the state, but it is a history of observations and actions. This is a bit of technicality, but in the end, this is most of the times when we do robot reinforcement learning, especially when we use vision or other type of perceptual signals, we need to formalize the problem in such a way. So what we have here is the state space. We have the action space, which are all the actions the agent can take. The observation space refers to what I was describing now, for example, images or tactile signals and so on. The Markov decision process is also characterized by one-step transition probability function, or also known the dynamics. Basically, if I take this action in this state, in what is the next state that I'm going to visit? And usually this is unknown in reinforcement learning. In Markov, this is unknown to the agent. Then, of course, you should have some sort of observation model in case you have these observations. And then you need also the reward function that I told you before, that you have to somehow design in order to guide the agent in discovering which behavior is good or bad. And the goal is to learn, again, this distribution, this policy of action given the current state. So again, here we summarize the goal of reinforcement learning, that it is to maximize the cumulative reward that you can see here. And as you can see, there is also this gamma parameter, which is a discount factor. And this discount factor basically regulates how much the agent wants to trust, how good would be the rewards that he is going to get into the future, or how much he wants to, the agent wants to, care more about the immediate, let's say, rewards that he gets in 1 step, 2 steps, instead of all the way to the future. Very important for reinforcement learning are the value functions. Here with capital G is just this cumulative, discounted cumulative return. This is how you were going to see it in the notation, and this is the usual notation used in the introduction to reinforcement learning from Sutton and Bartow, which is like the standard textbook for classical, let's say, reinforcement learning. For solving reinforcement learning, we need some functions. These are the state value function that basically gives you the value, the expected return, starting from state S after following the policy pi. There is also the action value function, or else Q function, which gives you the expected return that the agent is going to collect if it starts from state S, it takes action A, and then after that it follows policy pi. And in general, we need this Q function that contains this action here in order to extract the policy. Because if we are able to calculate the optimal Q function, so the Q function that gives us the maximum return if we follow the respective policy, we can now basically extract the optimal policy by basically taking the, in particular, I want you to focus here, by taking the action that maximizes this Q. So with the Rmax on the optimal Q function, we are able to do the policy extraction, basically to find which actions are the best to basically ensure that my return will be maximum, the rewards basically that I will collect in the future are maximum. One of the seminal methods for doing reinforcement learning is Q-learning. So the goal is to learn this optimal action value function that we said before. The intuition behind that is, as we said, how much total reward will I get if I take the action A in state S all the way to the future. And very important for updating and learning in the end this Q function that in the simplest case, this was just a table of values that you were just updating. It's to do the Bellman update. This is an iterative process where you try to update your guess of the Q function towards a target. So this is basically the Bellman update rule. You try to learn a new Q function by trying to push your current estimate of your Q function towards to update it, given this residual, this error here. This error is the combination of a target, that it is basically the reward that you received by taking the action A in state S, this is what you received from the environment, plus the discounted Qmax of the next state and next action. This Qmax is basically the value of the best possible action in the next state that you can get. And this basically tries to approximate what would be, so I take this action and it tries to tell you what will happen in the future, minus your current guess that you have. This is also, in some sense, regulated by the learning rate of how much do you want to change your Q. And what you can see already is that here it's an iterative process that is going to converge at some point, because the Bellman operator, basically what is happening inside here, is a contractive operator. So it has guarantees for at least the tabular case that is going to converge, and that you are going to find a solution, and you just need to tune these hyperparameters of the alpha and the discount factor that we discussed before. Everything is fine. This works very well for tabular and discrete tasks, but then when you want to apply this method for robotics, things become very difficult, because in robotics, in most cases, you have continuous state and continuous actions. And of course, the let's say the revolution happened in 2015 when the deep Q learning has been introduced, and this basically introduced a lot of tricks to make this iterative way of learning work, because you don't have really targets, and you can imagine that if you don't have really stable labels like supervised learning, this becomes a very, very noisy problem. So in Deep Q network, that what they did, and they applied it on the Atari games. They were taking as input some image observations, and these were passed through some convolutional layers followed by some fully connected layers. And because here the actions were discrete, for example, if you want to go left, right, top to play the game, this network would predict the Q values over all actions. Now, again, you can imagine that if you discretize the action space of robots, this can become super big. So you then have the problem of dimensionality, the curse of dimensionality. Now, some interesting tricks that were introduced that I would like to mention because we use them. We inherited these tricks, many of these tricks at least, for doing continuous reinforcement learning in terms of like continuous state and actions, was the introduction of replay buffer, where they try to decorrelate the data that you were basically collecting by doing a trajectory, by collecting all the trajectories in a buffer, what we call the replay buffer, and then you were sample randomly the data in order to break the correlations. They used target networks, which are frozen copies of the Q networks, to compute stable targets, because as you saw before from the Bellman operator, this residual error was always changing because your Q network, your guess, is always changing. So it is always trying to move towards something that continuously changes, and this is super unstable. So by freezing a copy of the model and using it as a part of the target made things more stable. And finally, how to do exploration. They used an epsilon greedy policy that basically ensured that we can visit the state space regions that where the current policy performs poorly. So it interchanged between using the current Q function for with some probability. You would select your current Q function to extract the policy, or you would use, for example, random actions, uniformly sampled actions, to ensure that you cover basically the space. There is a big taxonomy of reinforcement learning algorithms. Unfortunately, we cannot cover them in such a short tutorial. Here you can see the whole landscape. Of course, there is this part that are the model-based methods that they try to learn the dynamics that we don't discuss at all, but they are also very important and interesting to look into. We are looking into model-free reinforcement learning methods, and in particularly, we just talked about Q-learning. And now we're going to talk about policy optimization, because for robotics, in the end, you care about getting a policy. You want a controller, right? So for this regard, actor-critic methods, the ones that they learn both parameterization of the Q function and the parameterization of the policy, and they interplay with each other, is, let's say, the best way of getting policies for robotics. Soft actor critic is one of these methods. It uses two networks, the actor, that it is basically the policy, and the critic, that it is the Q function that we described before. And what is interesting and why it's called soft is that it introduces an entropy term. Basically, it adds noise in some sense into the Q function, so that it can inject noise when you extract basically your policy. In this case, what it does, it's a soft way of changing where the agent has to explore. So it is very efficient because also it has stochastic policy, so it can really induce use the noise in order to explore better the high-dimensional action spaces that we have in robotics. And here you can see an example of from the original paper that was in 2017 with this three-fingered hand trying to rotate this object. And obviously it needs quite some tuning, and it requires you to collect a replay buffer. On the other side of a methodology that has been used greatly in robotics is proximal policy optimization. It's very, very popular because it is very efficient and very easy to implement. And currently, with the use of a massively parallelized simulation, it's actually let's say, go-to algorithm to use also in robotics. It doesn't directly learn a Q function. It learns the advantage function, that it is basically the difference between the Q and the value function. Basically, it tells you, should I remember that the value function tells you what is the value of your, when you are in state S, of following policy pi, while the Q function tells you what is the value of being in state S taking action A that came from somewhere and then follow policy by. So this difference between these two values is called the advantage function, and this is what they are learning. What the proximal policy optimization, the PPO method uses is a clipping method that basically doesn't allow changing the policy too much. It really allows you to make incremental, let's say, steps towards improving your policy, but not really becoming super optimistic and do like huge steps in case you find a sample that looks good, but maybe in the end it's not really, really good. So this is really trade-offs, exploration and exploitation, how much basically you want to try new actions versus choosing the best known action. So as I said, it's very good for applying in robotics, especially if you want to use in massively parallelized settings. But if you want to do learning on the robot, like reinforcement learning on the robot, I would really argue that you need to use SAC, because it really gathers all the experiences that it has learned so far. It can also use, for example, part of the replay memory can be demonstrations, for example. So it is, let's say, safer in some sense to maybe to use for this kind of settings. PPO can also be used for real-world reinforcement learning, but again, you have to tune it very well. It has been used for the finger gating problem. As you see here, this has been done in OpenAI in 2018. But yeah, after that, they decided that they don't want to do robotics anymore, and they moved to foundation models, but then they will do a comeback in robotics, as we know now, by providing funds to several robotic startups. Some work from our lab where we have used these methodologies here. We have tried to control mobile manipulators that are more high dimensional than a classical static arm. We have to basically balance using the base and the arm concurrently. So we have to make both. For example, we can change the way that we solve this problem. Instead of doing a continuous control over the whole body by basically disentangling what the base should do and when the arm should be activated in order to do an action. And what we have shown is that these problems can become very difficult because of the exploration burden that you have. And therefore, we have found that introducing behavior priors can really speed up the learning and help learn difficult behaviors, even in mobile manipulators. So in this particular case, we introduced our reachability prior stemming from some classical methods that were actually coming from KIT, from the group of Tamim Asfour. And we used these inverse maps that you see here that basically try to guide the robot where to basically position itself in order to find the solution to reach a given target. And we have used this data in order to tell the agent which basically locations are kinematically feasible for reaching a target. And we use these ones in order to train our Q functions. And from stemming from this prior, we formalized a problem where we can manage both continuous and discrete actions. The discrete action would be, can I use my arm now in order to execute a manipulation task? Integrated these reachability priors, but we found still that the problem was very difficult, especially if you have to navigate complex environment, if you have a lot of collisions in the environment. So we also introduced boosting technique, a technique that basically breaks down your function approximator of the Q function into smaller, let's say, sub problems, in order to make your problem easier to learn and just boost the performance by starting from a simpler problem and then progressively learning a more and more difficult problem, such that you can, in the end, incorporate the full knowledge, if you want, from the experience that you have collected on experiencing increasingly more difficult tasks. And we have transferred this method directly into the real world for solving picking and also pick and placing tasks. And basically, the key takeaway here is that if you can really use robotic priors that come from the kinematics or the dynamics, you would see that it would really speed up the learning and the sample efficiency of your learning algorithms, because unfortunately, reinforcement learning methods are very, very data hungry. Now, to connect back to the diffusion models, we have also shown how we can combine the expressivity of diffusion models with the optimization of reinforcement learning. And in particular, we were interested in making reinforcement learning agents being able to discover multimodality and maintain it. Because one problem of reinforcement learning agents, due to the objective that they use for training, is that when they will find a solution that achieves the goal, basically they maximize their expected return, then they are going to say, okay, now I am done. I have the behavior, it's done. But this is not always the case, right? So there might be many different ways of solving the same task, and you want to keep this information in your policy. So we have introduced a methodology that tries to basically maintain a sort of multimodal memory of different experiences, and then use different Q functions in order to learn the value of the trajectories that belong to different modes. And all these have been used in order to learn a single diffusion policy that can use its expressivity in order to capture all the modes of behavior by using the diffusion models as our policy parameterization. And in this case, you can really be either take always the sample basically that dominates, or you can even steer your policy to get different ways of solving the problem. And we have shown in different decision-making problems, this is a locomotor robot where you have to learn to walk, but also learn to, okay, which goal should I go to? In this case, everything was fine because you could reach in either way all the goals, but we have shown that, for example, if you introduce now an obstacle in the way of the robot, it can decide to go to the other goal in order to achieve its task, right? So, and we have shown also this for robotic manipulation, where different behaviors could be learned and executed depending on what is the goal of the robot. What I want to make as a point is that introducing structure really helps robot learning, and in particular, both in imitation learning, as we see by, for example, introducing the SC3 diffusion fields, but also in reinforcement learning, because what we have to keep in mind is that our robots operate in a world governed by physics, geometry, and symmetry. Deep learning methods rarely exploit this structure. They try to learn everything from data, and basically embedding these priors into policies or models can provide us better efficiency, generalization, consistency, and can reduce the search space. So what we have been looking into is to how we can introduce priors, like in this case, we introduced symmetry as a structural prior to learn efficiently to control bimanual systems. Here we, instead of treating the left and the right arm as completely separate entities, using these methodologies, we used equivariant neural networks. We enforced the reflection operator. We learned separate tasks per arm, but then we were able to basically swap what each arm can do and learn, and eventually also share this experience and eventually distill it into a single policy that can control both arms that have learned through reinforcement learning. And we have learned complex texturous bimanual manipulation tasks that, as I told you, leveraging symmetry, we managed to be very efficient. So we needed much less data to be collected. And we were able to transfer this method by the distillation that I described before, because this distilled now single policy is able to control both arms without needing to know which arm has to do which task. So it really can straightforwardly decide which arm has to do which task. This finishes this part, and maybe for the interest of time, I will go through the last part and then take the questions. Because the last part will go over the foundation models and the future. It's shorter than the previous part because, I mean, this is now the current state of research. In the old way, basically, we're learning from scratch, or we needed experts giving us the data. In the new way, we try to use massive models pre-trained on broad internet data in order to build, let's say, a foundation. This is why they call them foundation models of general world knowledge. And then we try, in some cases, to fine-tune them, to adapt them to robotic tasks. There is a field that it is quite new. It started in let's say, the last 3 years, I would say, or so. The applications are various, from reasoning to basically reasoning planning, perception, but also action generation. It's a very active field, and we are going to see some examples. Some methodologies try to use large language models as, let's say, a brain, as a high-level task planner and reasoning engine. Basically, the function here of the LLM is to be prompted in order to decompose some human language goal into some concrete actionable steps. For example, here you see the Seikan model that tries to, let's say, I spilled my drink, can you help clean it up, is the example command. And then it provides some, let's say, reasonable steps of execution. However, these steps are not necessarily executable by the robot. They need to be grounded. So they need to, for example, find the sponge in the scene, ensure that the robot can reach it, ensure that there is an IK solution in order to execute, for example, a grasp, then navigate the robot and so on. So it really needs a lot of engineering. However, they can bring, let's say, generalization in the sense of, for example, being able to break down a very difficult task into subtasks where otherwise a human expert would have to do this. And they could also very easily integrate with humans, giving you a language goal instead of, a very structured and abstracted goal that it is common in task planning. Then we obviously want to use visual language models as the robot, let's say, eyes. These models like CLIP or CGLIP can provide some open vocabulary semantic features. They can provide, for example, in this case, in this word from Wolfram Burgard and Oyermes some years ago, they have shown that you can basically take the embeddings from these CLIP features instead of having direct labels and use them in a map in order to ask things like move first to the plant, and then you have a map that has now, instead of semantic labels, embeddings coming from these encoders that are also, let's say, more literate, right? Because they use these language descriptions. And finally, we have visual language action models. These are large transformers, like, for example, llama models that are fine-tuned on robotic actions instead of just the text. Usually, you try to take the VLM backbone, keep it frozen, or at least some layers of it frozen, and then add a decoding phase and fusion, basically, of, let's say, the frozen features, the tokens that you have from the VLMs and the actions in order to learn in the end a policy that can end-to-end control a robot. This is basically imitation learning with foundation models. Images and text go in, robot actions come out. OpenVLA, it's such a model. and in particular in newer efforts from various teams, also from coming, for example, from startups like Physical Intelligence, they try to have a single model that can do high-level reasoning, basically the sub-step decomposition that we saw before, together with the action generation in a single shot. But of course, the demos that they show look nice. However, in execution and how the fine-tuning is happening is basically really collapsing on the data that you produce. The benefits, though, is that you try to basically distill the semantic understanding and reasoning capabilities that VLMs have into action generation. However, one issue here is that you need the tokenization of the continuous robot actions into they have to be discretized into text tokens, for example, integers that have to be predicted and then detokenized into, again, continuous actions. And as you can imagine, if you want to execute fine-grained actions, this might end up into having problems unless you really engineer very well everything. Massive data are needed in order to train these models. Data like this OpenX initiative that tried to bring together different data sets from different embodiments and so on. However, as I said before, I don't see this being a viable solution in the long run because these models would either overfit a very specific way of behaving or a specific embodiment, or they will not be grounded. In our lab, we are very interested into grounding these foundation models into actionable affordances and into actionable features in general for acting in the real world. As I said before, these models lack physical precision. They struggle when they have to do contact-rich tasks or coordination of heavy, difficult tasks. They are very excellent at semantics like pick the apple, but they are not really very good at understanding the precise coordinates or like translating between images and actions. So grounding is basically the process of constraining a model's high-level plan to some actionable, valid regions of operation in the real world, or constraints, depending on the task. In particular, in our case, we focused on learning affordances. So we took a pre-trained VLM model and we added an adaptation module, and we decoded it into into affordance decoders that basically try to predict which part of the object has to be manipulated in order to execute the task at hand, and with which hand should you really execute the task. Here you can see an example. On the right side is our method that tries to predict where you should grasp with two hands the bottle in order to open it, versus a baseline that might, for example, for opening the bottle, it only predicts the cup as a single unimanual even action, while in order to stably execute this, you need to move the robot to execute the bimanual action. And this goes also to different other tasks. For example, here you want to steer the vegetables, and obviously you cannot grasp the spatula from wherever you want. And it actually makes sense to actually do it in a bimanual way. So you want to steer the vegetables by also carrying the pot so that it doesn't overturn while you are doing the steering action. Yeah, so this brings us towards the end. I think I'm a bit over time. I think the foundation models are powerful, but they have problems. So it's an open research direction. The problems are generalization and robustness. How do we go to the unpredictable real world? The seam to seam gap is still an open issue. Safety and predictability, robustness. How can we guarantee, for example, that the performance of these models will make robots operating safe around humans? An alternative view of what I try to show here is that if we use smart algorithms, modularity, and also priors, we can reduce the reliance on these massive real-world data sets. They are good as a backbone, but then how do we create efficient, sample-efficient methods, for example, by using priors, and architectures, for example, that as I showed you with respecting, for example, equivariance, so that we don't need to learn everything from scratch or have humans demonstrating everything. We need obviously also high fidelity simulation to model the real world. I think that these are very interesting research directions in our field. Yeah, and I think that going forward, we need to move towards reasoning and not just mimicking, and also actually causal reasoning. We can either go towards massive data, or we can really focus on creating smarter algorithms and more efficient learning paradigms. And I really believe that the future is hybrid, that you really need to combine robot learning, the learning policies, what I try to basically introduce you today, but together with classical robotics and more principled ways of introducing, for example, priors from geometry, physics, and so on. Yeah, last but not least, I want to tell you that we are hiring. So if you are interested in what we do, please